Okay, good afternoon, students. Today we are taking the second part of the properties of matter. Initially, we'll go through some of the important points which we would like to cover in this session, and then we'll come to the questions. So the quick revision for the important points, that is the first thing we are taking. So first slide, sir. Next one. So we'll talk about the viscosity. Viscosity basically is the inherent property of a fluid which opposes its own flow. When liquid is in motion, then a frictional force is present in it which opposes its own flow. To define the viscous force, we have one very simple model of fluid. We assume that the fluid is made up of layers, layer by layer. It is noticed that the layer which is almost close to the surface, the lowermost layer, is almost at rest. But as you proceed, you will find the velocity keeps on increasing. So we have a gradient. Gradient means the velocity is changing with the depth, and we have this quantity measured as dv by dz. We call this as the velocity gradient. So if I take a layer of an area A, then the viscous force is given as negative. Negative is because it's the opposing force. The coefficient of viscosity, A is the area, and dv by dz is the velocity gradient. Here it's very important to remember one thing, that SI system of coefficient of viscosity is 1 kilogram meter second. But sometimes it is expressed in Cbse system as poise. For example, water in a normal condition has a viscosity of 8 millipoise. Poise is a Cbse unit. SI unit is bigger than the Cbse unit by a factor of 10. Right? Whenever it is required, you can make use of it. Next slide. See, in a previous lecture, I told you that you can use Bernoulli's theorem for study of the flow of liquids. Bernoulli's theorem is basically the energy concept, but there is a condition. It is applicable only for those fluids which are ideal. That means there is no viscosity. What will happen if I have viscosity? One thing, I cannot use the Bernoulli's theorem. But can I use the equation of continuity? Yes, we can use the equation of continuity even if the viscosity is there, right? But there is a formula to handle the motion and is given by Poiseuille, known by his name, Poiseuille's formula, according to which if there is a tube and through the tube the liquid is flowing at a rate Q, which is nothing but is the volume per unit time, it depends on the pressure difference P, the radius, coefficient of viscosity, and the length. Notice this very important thing, that the radius comes with the power 4. That means slight change in the radius is going to bring a large change in the rate of flow. Coefficient of viscosity is in the denominator. That means if there is more coefficient of viscosity, the rate of flow is going to be less. Of course, the length also plays a role here. To understand this very relation, I would like to give you its analogy with the current. In your 10th class, you all have gone through this Ohm's law, the relation between the current and the potential difference. We have a similar concept here. But try to understand the analogy so that you can make the attempt in a more convenient way. See, if I make, say, flow of fluid on this side, and the flow of charges on this side, then when we say current is basically the rate of flow of charge. So we represent normally this by dq by dt, saying that q is the charge and t is the time. We have a similar kind of a concept in this case, and that is the volume flow per unit time, that is Q. This is the volume per unit time. You can say in this case, whatever is the role of the current, in the flow of liquid case, the same role is played by the rate of flow, Q. In this case, we have potential difference that of course is given by a cell. If I make a cell like this, or maybe a battery where there's a combination of cells, so this bigger side means the high potential and smaller side indicates the lower potential. The same role is played in this case by the pressure difference, which I am representing as P. P stand here for the pressure difference. That means if I have a tube here, and suppose I have more pressure at the inlet, let me call this point as A and this point as B. If somehow by help of a pump, I generate higher pressure at A and lower pressure at B, then I'll get the flow from high pressure side to low pressure side. As we say that in case of this cell concept, when you have a resistance, the current always go from high potential to low potential side. So you can make the two as they are in a similar footing, but with a small change in the parameters. In this case, we have a quantity known as the electrical resistance. That is the resistance which any conductor will offer to the flow of charges through it. That is nothing but is the, in a simple relation, that is the Ohm's law, that is the potential difference divided by current. We have exactly the similar concept here. If I ask you what is the resistance in the flow, I'm putting it this as RF. From the analogy, I know that V is the pressure in this case, and this rate of flow is nothing but is equals to Q. If I replace it there, look, if I replace the expression for Q, the P will be out of the scene, and this then will become pi R4 divided by eta into L. Why I'm saying that you should remember this? There is a very special reason. We have certain well-defined relations in case of the current electricity. For example, if I have a resistance, say R1, connected with another resistance, say R2, and they are in series. When I say the two resistors are in series, I always say that the current flowing through them is same. If I is the current flowing through this resistor, then same current flows through the other resistor also. If I make use of this concept to find out the equivalent resistance, we have a very common formula known to everybody, that is equals to R1 plus R2. I have the similar situation in this case. When they ask the question, they give you the similar type of a thing. For example, if I have two pipes connected such that they are in series like this, obviously the liquid is flowing from one end and is coming out from the other end. I treat this type of a situation saying that the quantity Q, that is the rate of flow, that is equivalent to current in this case, is same through this pipe as well as through this pipe. And at the same time, if I ask you what is the R equivalent, R equivalent once again means I'm talking about pi I4 eta L. In that situation, I say the R equivalent in this case is going to be the resistance to the flow offered by 1, resistance to the flow offered by the 2, they will add up. The quantity that will add up. The total resistance offered by this combination is going to be given by the similar formula. If I have two resistors in parallel, say R1 and R2, in this case, we say that the potential difference across this and across this are going to be same. If I have a similar type of a situation in our case, if I have a pipe and I connect another pipe and I permit the liquid to flow through both the pipes, I say they are in the parallel combination. That is the situation here. I allow them, the current say I1 is passing through this, current I2 is passing through this. I say, okay, here we have Q1, Q2, the rate of flow, the equivalent. What then is the total current coming out of it? That means total rate of flow. That is going to be Q equals to Q1 plus Q2. Exactly what we say here, that the total current I is equals to I1 plus I2. See, this analogy is very useful in solving the problems because we have well established formulas for this. You think when the question is asked from you on this line, and that will help you to do the things in a simple form. In a nutshell, I would like to tell you that if there is a series combination, Q is same through the two pipes. And when they are in parallel combination, the total rate of flow is going to be the sum of the rate of flow through both the pipes. However, the pressure difference, pressure is equivalent to potential difference. In a parallel combination, the pressure is going to be same on the both sides, right? So that will help you to handle the problems based on this. Coming to the next slide. This is a very important law associated with the viscosity, that is the Stokes law. See, can you think of that these raindrops, when they are coming from the cloud, they have to travel thousands of meters to reach the ground? Let me take it with the help of an example to demonstrate to you that what is the role of the viscosity. If I assume a cloud to be at some height, let me take for example that is equals to 2 kilometers. Just I'm taking it with for the simplicity, right? And a water drop starts from here. When it reaches here, it is moving under the acceleration due to gravity, g, and for simplicity, let it be 10 meters per second square. The velocity with which it will hit the ground from the one-dimensional motion can be obtained by a simple formula, v equals to under root of 2gh. Let's put the value and see what happens. 2 g is the acceleration due to gravity, the h, that's the height, and that is 2000 meter because I have taken it as 2 kilometers. If you solve it, you will find this comes out to be 200 meters per second, and that is equivalent to 720 kilometers per hour. This is such a high velocity. With this velocity, if this drop hits the ground, it is going to damage any vegetation or even a human being if is there. There is no possibility of his survival. But we don't have this situation in actual. Why? Because we have air which is providing enough frictional force when it is coming down. That's why these drops, they reach the ground not with a very large velocity, that is quite safe velocity. That's why we have vegetation on the surface of Earth or even the human beings. But how to handle it? For handling it, especially for a spherical body, see, I'm using a word especially for a spherical body, there is a law known as the Stokes law, which says that if this is going down, there comes a frictional force in the upward direction, and that frictional force is equals to 6 pi eta r into v. This factor of 6 pi is because of spherical drop. Eta is the coefficient of viscosity, not of the water, but of the fluid in which it is moving. R is the radius of this drop, and v is its instantaneous velocity. See, let's understand this point in detail, what I'm saying. Let's see the process step by step. A drop starts from the top. Its initial velocity is 0. Its initial velocity is 0. When initial velocity is 0, the force of friction, let me put this as Ff. Ff means force of friction. Because of the formula, since V is involved here, V is 0 means there is no force of friction. So force of friction is 0. So what is there then? There are two forces. One is the weight, mg, that is the weight of the body, and there is another force that we call as the buoyant force. That's the upward thrust. Because air also is a fluid, so where anybody present in air is going to experience an upward thrust, and this upward thrust is there. If the weight is more, this body will obviously, or the drop will obviously start moving in the downward direction. If it is moving in the downward direction, because the weight is more than the force of buoyancy, then what happens? It is going to gain velocity. It is under acceleration. Its velocity is continuously increasing. When its velocity increases to such a value that the buoyant force and the force of friction acting on it are balanced by the weight, the total force on it will become 0. That is what we call as the equilibrium. Now whatever is the velocity, we call this velocity as the terminal velocity. If I have to plot a graph, say with time and the velocity, it initially starts with a 0 velocity, this we assume, right? The velocity increases, but this increase finally ends at a value, we call this as the terminal velocity, right? So we have a formula for the terminal velocity. The next slide, sir. Previous one. There is. Okay, I'll put this is the terminal velocity is already there. So let's understand this. 2/9. This is for the spherical system, right? R square, the radius square. Rho is the density of this fluid or the drop. And sigma is the density of the medium under which it is moving. And eta is the coefficient of viscosity. Please try to keep that in mind. Once again, R comes with the power 2. Whenever you have these powers going high, you try to get one thing in mind, that they are going to put more effect on the value of the quantity you are talking about as compared to the other quantities, right? G is acceleration due to gravity, G is acceleration due to gravity, right? So this is the expression for the terminal velocity. It means the terminal velocity is going to, that is the maximum possible velocity which the drop will have, and the velocity is not increasing the way we have taken in this case. It is not increasing like this. It is in fact is increasing like this. So thanks to viscosity of air, which is preventing us from a damage which these water droplets can do, right? Next slide, sir. There is a very important and interesting property of a fluid, but when fluid is at rest, and that property is the surface tension of the fluid. Why this surface tension is there, number one, and how we count for it. Surface tension is basically due to the forces these atom or molecules they experience when they are in fluid. Because fluid or liquid is such a, say, phase of the system where the atoms are not very far off. They are at some distance, that is a finite distance. So at this finite distance, they have some kind of bonding. If I draw an imaginary line, look how we handle it. If I draw an imaginary line on this liquid surface, the atoms present on it are going to experience a force from the other atom or molecules in the surrounding. If I calculate the force only in one direction, please don't add this vectorially, because if you add vectorially, it is going to give you 0. So what I do is I deliberately try to add up the force on one side and divide by the length. Because if everything is in equilibrium, the total force is 0. but that force is parallel to the surface, or you can say even tangent to the surface. So adding that force per unit length, that is what we call as a surface tension. This is one way. There is another way of defining the surface tension, and that is based on the surface energy. But before that, I would like to show you a small video where you can find ball pin made up of steel is floating on the surface of the liquid. Can you run that small movie? The big question is, can a metal float? Look, can you stop it at this stage? Just stop it at this stage. What you can notice that there is an ball pin which is made up of steel. The density of steel is much higher than that of water. It is not hollow from inside. It is a solid, say aluminium, steel ball pin. I kept a small blotting paper in the water and I put this ball pin on the top of it. That is deliberately done not to disturb the water surface deliberately. After some time, what I'm doing is I am pushing this paper inside the water, because now this is heavy because it absorbs the water, so it easily sinks. And you will notice that if I keep the surface undisturbed, this steel pin keeps on floating on it. Continue this. Now look at this. The paper has gone inside and this is floating. If you can notice, that is a small modification near the surface of it. You can just notice this one. So this all is because of the surface tension. And surface tension is a force. This is a simple demonstration for you that this is enough force to keep the ball pin floating on the surface of the water. It is not because the part of this, close down. It's not that the part of this is inside the water and there is a buoyant force balancing it, the weight of the ball pin. It is not like this. It is a surface tension. It is like a stretched membrane, as if, say, if I ask all of you to just stand around a sheet and ask you to just pull the sheet from all sides, you will find that the sheet becomes straight, stretched, and I can put some stone or maybe anything heavy on the top of it, and that is gets supported. So this what is a property of the fluid, and we call this as a surface tension. It plays a great role. All liquid drops are spherical because of this property, right? Next slide, sir. Now, I was telling you that there is another way in which the surface tension can also be defined. If I take a wire like this, which is in the form of a frame, and I put some, say, liquid, maybe a soap liquid or soaps dissolved in water, and make a small film. I dip it and take it out, I'll get a film. If this is a slider, ml is a slider, if I'm pushing it in this side, I find that it is not easy for me to pull it. Because of the surface tension, this from all ends, this liquid is trying to make the area as minimum as possible. So I have to do some work. My work goes in the form of what we call as the potential energy. If I'm doing a work to stretch the film, my work goes in the potential energy form. How much area I have increased? If I have moved a distance x and say this length is L, the area which I have developed is equals to L into x multiplied by 2. This is very important. When I talk about the surface and I have a film, if I have a film, I have a surface on this side as well as I have a surface on the other side too, which I should not forget for solving these type of the problems. So there are in fact two surfaces. One is from the top, other is from the bottom, if it's a film. So I have taken the area as twice Lx. And similarly the force, the length is not only L, the length also is twice of L, because surface tension, the force from this side, and from the back of it also is there. So this ratio is also called the surface tension. So remember like this, the surface tension is force per unit length as well as it is energy per unit area, right? So they will help a lot, and especially this particular equation where it says that this is the potential energy, let me put this as U, and the area, normally it is taken like this, that if there is a change in the potential energy by changing the area, we have this ratio. It means if I want to know how much energy I have changed, that can be obtained by taking du T into delta A. Delta A is a change in area. But while taking it, I must not forget, I have to take the area change from both the sides if it's a film, right? Yeah. Not always, because if there is a, suppose there is a liquid drop which is spherical, then only the surface area is 4 pi r square. But if the same size bubble is there, then there are two surfaces. This is important. So yeah, if there is a drop, it is only having one surface. But if it is a bubble where the thickness is not very large, I have one surface from the inner side and I have another surface from the outer side. If I assume the radius for inner and outer will be very close to each other, let it be average radius is r, then the surface area of this will be, surface area is 8 pi r square, where in this case I have to take it as only 4 pi r square. So these corrections you should be very careful, and definitely the wrong answer by taking a wrong area, whatever you may get, that must also be there in this, in your options, right? So we have to be extremely careful for this type of the problems. Next slide. Due to surface tension, we have one very interesting property. We have an excess pressure. Say in case of a drop, the excess pressure is 2T by R, where T stands for the surface tension. You may find in some cases the people use T as the symbol for the surface tension. In some cases they use sigma as the surface tension. That doesn't matter. The symbol can be any. But the main feature is that how the things are related. Excess pressure is inside. Why excess pressure is inside is very important to understand. See, from this relation I know that the energy is directly proportional to the area. Every system tries to minimize its energy. So to minimize energy, we should minimize the surface area. How can we minimize? We have to reduce as much as possible. While doing it, if I am reducing it, I am putting an additional pressure inside. So this relations you have to remember that for a drop, the inside pressure is more by a factor of 2T by R. If I ask you how much is the total pressure, it will be atmospheric pressure plus 2T by R. But if it is a bubble, as I told you, bubble has two surfaces. One is from the outer side and other is from the inner side. So that difference comes out to be 4T by R. But R here stands for the average radius. R is not the radius of any one of the surface. It is the average radius, because normally these bubbles are very thin as far as the surface part is concerned. But very interesting situation. When it is a bubble inside a liquid, it is a bubble, name is bubble, but it is inside the liquid. For example, if I have some air bubble inside the water, or you may have a carbonated, say, water in soft drinks, you may have carbon dioxide bubble formed inside the, say, that liquid. In that situation, since we have only one surface, then that will be only excess pressure is 2T by R. So you have to be very careful. You read the language of the question carefully. Are they saying the bubble in air, or they are saying bubble in liquid? If it is bubble in liquid, the surface is 1, so pressure is going to be 2T by R only. There is another very interesting formula to remember. Inside a cylindrical surface, I'm not going in the derivation part of it, but if it is a spherical in shape, the things goes as 2T by R or 4T by R. But if it is a cylindrical surface, it goes as T by R. And there is only one surface for which we are talking about. Only in the case of the bubble in air, we have two surfaces. So these relations are very important in handling the problem, because they sometimes mix up the question. Sometimes they say that the two drops or two bubbles, they are combined together, they coalesce together. These type of the problems can be handled if you remember this type of pressure difference there. Next slide. Surface tension has one very important property related to it, and that is the angle of contact. See, in some liquid, when I put in a capillary or maybe a thin tube, we find the surface is concave, and in other cases we find the surface is convex. That is basically due to the difference in their cohesive and adhesive forces. I'm not going in that detail, but more important thing is that how we take the contact angle. Look, from the wall, I'm measuring the angle up to the tangent drawn on the surface, which is at the point of contact. That's why this angle is called the angle of contact. In some cases, it is acute. Say, for example, in case of the water, in glass tube, we call such liquid as the wetting liquid. And when it is obtuse, see again, the angle is taken from the wall up to the tangent, but through the liquid. Through the liquid. Don't take this angle. This is a requirement that you should measure the angle through the liquid. If it is obtuse, say for example, in case of the mercury, we call this liquid is a non-wetting liquid. Wetting liquid, when you put it on a glass surface, you might have noticed that the water droplets, they take some, say, hemispherical structures on the surface of the water. But when it is a case of the mercury, it always takes a spherical shape, right? Close to it. So this angle of contact is quite important when we handle the problems of the surface tension. The very important relation for the capillary rise, the number of questions are there on it. When we talk about the wetting liquid, we notice that the liquid rises up to certain height only. And this height is given by the relation H is equals to 2T by R rho G cos of theta C. Let's recognize everything. T is the surface tension as we discussed. R is the radius. Radius of what? Not the radius of the surface, radius of the capillary. Rho is the density of the liquid, and G is the acceleration due to gravity. And then we have a factor of cos theta C, and theta C is the contact angle. In some questions you may find they are giving you the radius of the meniscus. If the radius of the meniscus is given, then the same relation will take a shape like this. H is equals to 2T by R rho G. Then don't use the cos theta factor here. This R then will be the radius of the meniscus. That means the surface, this surface, say for example, it's a concave surface. If this surface I take as a spherical surface, then the radius of this is going to be capital R. So we have to be extremely careful. Is the radius of the capillary is given or radius of meniscus is given? If radius of capillary is given, then you have to use the cos theta C, right, in the multiple. But if the radius of meniscus they have mentioned, then don't use the cos theta C. There's an interrelation between them. The same formula can be used for the non-wetting liquids. That means when theta C is going to be obtuse, in this case we say the capillary rise. But if I put the theta C obtuse, see cos function in the second quadrant is negative. So automatically the value of H comes out to be negative. That means it is not a rise, it is a fall of the liquid in the capillary, right? So this is the important formula. Everything you must keep in mind when we handle the problems. We'll see to it, right? Next one, sir. Coming to the elastic properties of the material, I'm quickly revising it. Already you have a session on it in detail, but let's have some important formulas before we attempt questions. So this is the stress and strain and the modulus of elasticity in a various situation we are given. When we have a normal stress, that means we are having a force applied along the length. We normally write this as F by A, where A stands for the area of cross section. Say for example, if I have this as my wire, then this is going to be the area of cross section. I'll not take the curved area. I'll take the area of cross section. We call this as the normal stress. In the same case, we normally talk about a strain as change of length to the original length, because length is the main parameter in it. So we take this. And if you take the ratio of the two, we call this as nothing but is the Young's modulus. If I do not change the dimension, but I change the shape, say for example, if I have a cube, I try to shift the cube, right, by putting a force on the top of it, then we call this stress as the tangential stress. In this case, we have the force divided by the area. Here we must understand this is not the area of cross section. If I have a cube like structure like this, and somehow I fix it from the bottom, and I apply the force on this, on the surface to change the shape. I want to bend it like this. I want to bend it. In that case, I'll count this area on which I have applied the force. It is not the area of cross section, right? So we have to be very careful in measuring this area and putting it in the value for A. So, and in this similar situation, we have a strain known as a shear strain, which is basically is this angle or angular shift which we have, right? It is not the length change, it is the shape change. So this is the angle which we call as a shear strain. And if I take the ratio of the two, that means the tangential stress and the shear strain, this ratio is nothing but is called modulus of rigidity, normally written as eta, right? Symbol they can always change. Now there is another interesting stress. We call it as a pressure stress. It is also force divided by area as by definition, but area, which area we should take? We should take the surface area this time. If the body is getting the force from all the sides, then take the area which is the surface area. And in that case, we are more interested in the volume change. We call it as a volume strain. That is a change of volume to the original volume. And the ratio, we call it as the bulk modulus. Notice one very interesting thing, that we have a negative sign only in the case of the bulk modulus. We don't have this negative sign in the two cases, but we have a negative sign here. It's a very simple reason. We want to keep K positive. So obviously when you apply a, say, force on a particular, say, liquid or maybe solid, you have a reduction in its volume. So when you have a force on it, there is a reduction in the volume. So this negative and one negative from this side, because of the reduction of the volume, will give you the K positive. So all my moduli of elasticity, that means the Young's modulus, modulus of rigidity, the bulk modulus, they all are positive. None of them is negative. We have another important physical quantity known as the Poisson's ratio. This is basically the ratio of the transverse strain to the longitudinal strain. What is the meaning of this? If I have a wire, and if I stretch this wire by applying the force from the, say, base, I get the increment in the length. But at the same time, I notice for most of the metals, there is a decrease in the radius. It becomes thin, comparatively thin. It becomes longer, but from the radius point of view, there is a decrease in the radius. So this is a transverse strain, which is nothing but is the change of radius to the original radius, dr by r, and divide by the longitudinal strain, which is dl by l. And again, you see what I have here, negative sign. Normally we see that when there is an increase in the length, there is a decrease in the radius. But let me tell you, this Poisson's ratio theoretically lies between 0.5 and -1. When it is -1, what does it mean? It means if I am increasing the length, its radius also is increasing. Certain materials are like this, right? Certain organic materials are such that when you try to increase the length, their size will increase. So theoretically, sigma cannot even be 0.5 or more. It cannot be less as -1 or even lesser than that. So this is a theoretical limit. So sometimes they ask the question even from this value, right? For most of the metal, it is 0.2, 0.3, it is on this side. But negative also is possible theoretically, right? Next, one of the very important law from elasticity that is known as the Hooke's law. If somebody try to, this is stress, and some spelling error is there. It is stress and this side is strain. If I take a material, say a metal, normally we have this type of a typical pattern of the variation of stress with strain. For this initial part, it is straight line. This region is known as the elastic region. From then onward, it is not showing the linear variation. So our Hooke's law is valid only for this part, which we sometimes called as a proportionality limit or proportionality region or elastic region. Though there is a small difference, let's not go in that detail. So for this part, we can make use of this law, which we say that this is stress proportional to strain, right? And as stress, as we know, that is the force per unit area. That may be area of cross section, that may be surface area, depending upon the situation, and same is the case with the strain. So this is the main law we have here, but applicable only for this region, that is to be remembered, right? Now very important, although proof once again we are not going in that. These are the interconnection relation between the Young's modulus, bulk modulus, the Poisson's ratio, Young's modulus, modulus of rigidity, and the Poisson's ratio. See, I told you that the Poisson's ratio cannot be even 0.5 or less or more than that. You can check it from here. Look, if Poisson's ratio sigma is more than 0.5, then this is going to be negative. Neither K nor Y. None of them can ever have a negative value, right? So these are certain restrictions we have from this relation. Similarly, sigma cannot be less than -1, because the moment you put this less than -1, the whole term will become negative. Either Y is negative or eta is negative. This is again is not possible. So these relations you can remember, right? These are interconnecting relations. Sometimes they give you information for Young's modulus, bulk modulus, and they'll ask you what is Poisson's ratio. So interconnections, you can handle it. So this you have to remember, right? Proof we are not touching at this stage. Next one, sir. Yeah, there's one more. That's the application part of it. And questions are asked even from this portion, though it's not covered in the Cbse syllabus, but sometime in competitions they ask for that. What is this? Bending of beams. Let me make one point clear here. There is a difference between beam and pillar. If I have a structure which is kept horizontal for support, say for example, I want to support the roof of a building, I have to have a horizontal structure made up of steel or concrete. We call it as a beam. It can even be a metal rod, right? On an experimental level, it can be a metal rod. Suppose I fix it or I support it from the ends. So this end is A, this end is B, and from the middle I put a load W. From the middle I put a load. What normally we notice? This bends a bit. How much will it bend? It is this depression at the middle, delta, is given by the relation, and this relation is given as W L cube B D cube Y. Let's understand all of them. W is the weight, L is the length, this is the length. And what is B and D? If I look at its cross section, if I make a three-dimensional picture like this, then this thickness, that is the vertical thickness, that is D in this case, and this width is W. I'm actually giving you this formula when I have a rectangular cross section. A rectangular cross section where the width is W and thickness is D. Please do notice one thing again. D comes with the power cube and is in the denominator. So if I want to minimize my delta, what immediately I can do? I have to increase the value of D, because increasing the value of the D will help me. If I take this as a thicker one, I'm going to reduce the depression produced in it, right? So this actually is a very important formula for the designing of the bridges or even the construction of a building. So that's why sometimes this is asked in the examination, right? So remember the main formula, that is more important. So sometimes what they do, they change the W, or they change the length, or they change the D, and then they compare the two situations, right? Very simple type of the question, not very detailed questions are there from this portion. So next, can I make use? Achha, this is, yeah. One more formula, once again, not from the syllabus you have covered, but again to remember, if I have a rod, and I fix it from the top, say for example this one, I keep this pen and I hold it from here, this place, and I twist it. Twist means I'm producing a torque to make this lower portion to rotate. Then we have what we call as the angular twist made. So this twist angle is the angle which this lower end is going to have when I make it to twist, the angle which it turns. And this angle is given by the relation 2 tau, the torque which you have produced, length pi eta r to the power 4. Once again, have a notice on this part. In some cases it comes with r power 4, in some cases it comes with r power 2, right? Be careful. That will be of great help for you to handle the problems based on this. Or you can write torque, that is nothing but the similar formula. But we have to be very, very careful. This angle is not the strain, angular strain, it is the angular twist. And remember, if everything here is taken in the SI system, then this angle is always in radian, not in degree. They may give you the question with angle of twist in degree. You have to convert it into radian, and one simple relation we have, if I have, say, the phi given me in degree, then I can change it by simply multiplying with 2 pi and dividing it by 180, because degree will go. Or you can take pi by 90 there, pi by 180. This is not 2 pi, it is pi by 180, or you can solve it to put the value there in pi, that is the angular twist, to handle this problem, right? Next. Now we come to the problem. I hope this quick, say, run through the various formulas will help you. Now coming to the question, I want that you should try this once again, though they are based on some numerical calculation, but do it. The first question reads, if work done in increasing the size of the rectangular soap film from size 10 centimeter cross 6 centimeter to 10 centimeter cross 11 centimeter, put the centimeter here, centimeter is this much, then what is the surface tension of the liquid which is made up, which is making the film? Do it. A small calculation required. Be careful. Few informations are given in centimeter. This is 6 centimeter, right? 10 centimeter cross 6 centimeter. And some information is given in SI system, that is 2 into 10 to the power minus 4. This is minus 4. So you have to be very careful, right? While doing the problems where the numerical calculations are involved, unit is very important criteria. Through with the answer? See, I told you in my previous lectures also, whenever you have a mathematical calculation done, try to minimize the steps involved in it. See how we can do it. We can do it by quickly doing it, the calculation on paper also. But before that, you just try to do it, even if we can do it without much calculations. Look, this is going to be 60 centimeters square. Try to learn the method of handling the multiple choice questions. And this is 10 multiplied by 11. It is going to be 110 centimeters square. What's the difference? 50. Actually, in fact, what I am doing, in my mind, I am using this formula. The energy change is equals to surface tension multiplied by the area change. Is it clear? From the given information, I come to the stage that the area change is 50. But if I have to do it in SI system, right, because all my answers given are in SI system, I will do by putting a 10 to the power minus 4. Agreed? But one precaution, if I have some surface, then I should count not only the surface from this side, I have to count the surface from the back side too. This is the important precaution which you must keep in mind at this stage. So in fact, the area you have changed is not 50, it is 100. And this then is given 2 into 10 to the power minus 4. So this becomes 10 to the power minus 2. 10 to the power minus 2 on this side will make it only 2 into 10 to the power minus 2. So your answer is going to be the D in this case, right? If you do it wrongly, then you may land up to a difficult situation, right? So this is how these type of the questions are answered, right? Is it clear? See how we look to it. When you change the size of this film, you are in fact changing the area, surface area of the film, but not from the top, you are changing it from the bottom also. And then rest is a mathematics. But my advice to you is, when you have these type of calculation done, try to do it in your mind more than what you do in a piece of paper. But you have to be very, very careful while doing it. So I hope this point is clear to you. Next question. I think this you can handle easily now. This is answered. Skip this one. Yeah. The question says that you have to calculate the work done in blowing a soap bubble from radius 2 centimeter to 5 centimeter. Informations are given. The surface tension of the soap solution is given to you, and they are looking only for the work which you have to do. But please do remember that it is case of a soap bubble, and I'm sure that you remember it. There are two surfaces, one from inside, other is from the outside. Do it fast then. You're taking too much of time. See, the trick is to handle. No, it's not A. It's not A. Even it is not D. B is also not. So now only one thing is left out, that is, let's do it and let's try to learn the technique, right? Mathematically we can solve. If this question is given in the CBSE, you can do good steps to handle it. But it is a multiple choice question. We should not waste much of the time in the calculation. I'm sure this you must have reached upon, that work done is equals to surface tension multiplied by area change. Agreed? Because this is the potential energy difference, and whatever the potential energy difference is, that much amount of work I have to do. I have to get this area change. Now what is the area of a bubble? What is the area of the bubble? Formula. It is 8 pi r square. Why I'm insisting on this 8 pi r square? Because there are two surfaces. I already have taken the count of it. Please don't multiply by. Then we have to multiply by surface tension. That is the area change final minus initial square. This all calculation you have to do in your mind. If you need, you may write, but my advice is that try to minimize the written work. If you can do it faster, then it's nice. See, this is given to you. We have to be very, very careful for the powers there. Are they in the SI system? Look, 6 into 10 to the power minus 2 is given in the SI system, no problem at all. 8 multiplied by 3.14. But when I come to the radius square, I'm going from 2 to 5. That means 25 minus 4 into 10 to the power minus 4. Agreed? Right? That much is clear. I have to solve it. A calculation which is appeared to be a bit lengthier. But there are some times that some informations are given in such a way that you can handle it easily. 10 to the power minus 6 is not possible because you have large values involved in it. So 10 to the power minus 6 factors are out from it. So one thing you must keep in mind, that B and D cannot be the answer. Check it. We have to be intelligent, right? You can solve it, I'm sure. But if you take more time, then you can't save time for those questions where you have to do the calculation, lengthy calculations involving calculus in it. In those cases, you'll find the shortage of time. So better to do these questions with intelligence. Minus 4, minus 2. But other numbers are quite large. So definitely these numbers when multiplied together are not going to give you value of the order of 10 to the minus 6. What is left out then? A and C. Some answer must be there between A and C. This is why to write 3.14. Can't I write this as 22 by 7? From where I have reached, look at this. 7 will be out from here and I can put the 3 here. You can make your calculation simple if you look at it with this intention that you have to make it simple. You can do it. Somehow it's possible. In some cases, if it is not possible, then you go do the calculations in a systematic manner. Look, now we have it. So this is nothing but is 48 multiplied by 66, right? And then we have 10 to the power minus 3 to it. Can it ever give me 1? What it will give me? Look at this, 6 and 4. Or you can treat this as 50. So if it is 50 and this is 60, let it be somehow managing. It's not going to be 300 or otherwise you do it. So out of A and C, which will be your better answer? C. Okay. This is a multiple choice question setup. I'm not saying this, what I'm telling you is a very correct method. It is not correct, but it is definitely faster method. If I select my options and then I do the necessary calculation only, I can reach to my answer correctly and with a lesser time. So this is the, say, one trick which you always keep in mind while even practicing questions from your book, right? Time factor is very important. Okay, next question. Skip that one. That is a systematic way. Okay, a new variety of the question. What it reads like this, that there are 27 identical drops of water are falling down vertically in air, each with the terminal velocity of 0.15 meter per second. They combine to form a single bigger drop. Assuming other conditions to remain same, the terminal velocity of the combined drop is. Try to do it with a method which I told you, right? You have to attack it aggressively and we have to do it faster. Keep it in mind what is happening. This picture must come in your mind that there are many drops. I'm not taking 27. They combine to form a bigger drop. What has changed? Which factor has changed? Radius. How much it has changed? That is 3r. If each one of them is having r, this is 3r. Why I'm saying so? Look at this. 27 4 by 3 pi r cube. That is the total volume of it. When they combine together, they have 4 by 3 pi capital R cube. If I simplify and take a cube root of it, that I'm going to get this value as 3 of R. This you have to think, and you think it faster. Okay, then what has been asked in this case? Terminal velocity. Quickly remember the formula. He says remaining things are same. Which factor is changing? R. Do you remember? Your terminal velocity is proportional to R square. Proportional to R square. Rest is same. Viscosity is same. Right? G is same. What are the other possibilities? Please don't go for the correct formula. We know that the formula for terminal velocity is 2 by 9 R square G rho minus sigma divided by eta. Why to write all this? You write the minimum. Vt is proportional to R square, and since this has become 3, so it's going to be 9 times, right? When it is 9 times or 9 times of 0.15, I think now it's not difficult for you to answer. 1.35. That is your answer. 1.35a is your answer. So, say my now point here for you is that we have to handle it. That's true. We can handle it by doing it in a systematic manner as we do it in Cbse. If the same question comes in the Cbse as a numerical problem for you, they expect from you to write the formula also. Then I can't skip. But in multiple choice for this case, I do remember each and every necessary condition from the formula, but no need to write the formula completely. Then remember what factor is changing. But when you do that, you please ensure the other should remain constant. G should remain constant. Okay, he has given densities and all that, viscosities, but radius is definitely is going to change, and that is a factor which is asking. So we have to handle the problem from that point at which he is pointing out, right? You have to reach it faster. That is an important thing. Next question, sir. This is the solution. Skip it. Now, he says that height to which a kerosene is a straightforward question. I just for the practice sake I have given. Height to which the kerosene will rise in a glass capillary tube of 0.2 mm diameter. Look at this. So the tricks they play the tricks in giving you the units. They play the trick in giving you the quantities, related quantities, rather than the quantities used in the formula. I have the radius of the capillary in the formula, but they have given me the diameter. I must keep that in mind. Rest is given. Do the thing faster and get the answer as quick as possible. But here is a point which I would like to mention. Look, my all options are given in centimeter. There is no harm if I keep all my quantities in the CJ system. There is no harm. Do it. I can do it otherwise also. There is no such issue in it. This is from the same,
Yes, sir.
even odd. Okay. Now, these are the question, I think, not for this
No,
particular
not
part.
the function. Green color are all first sessions.
Acha, first session. That's fine.
No black color is there.
Acha. Acha. Question number 2. I'll do that in at the end, right? So that every question I'll take in the end. Answer is B. Small error in it. Answer is D. Very good. See, these numerical value calculation require that you identify the units in a proper manner and go for it systematically. Few quantities are given in CGS system, few quantities are given in SI systems. Either you take everything in SI system and go ahead with it, agreed, or you do everything in the CGS system, whatever the way you want, right? The formula is very simple. The H is equals to 2T by R rho G and cos of theta C. That is required. This time I require cos theta C. I have not given you the radius of the meniscus. There's a difference. Radius of capillary is this radius. This is the radius. But when we talk about the meniscus, meniscus means the surface. The radius is different. I have to complete this sphere and then I have to talk about the radius. That is the radius R. So this time we are taking the radius of the capillary. So I have to continue with this cos of theta C factor there for correction that is required. Rest is simple. Do you want to do it in SI system? If you want to do it in SI system, then the surface tension is given to you 0.26 as SI system. Now I am maintaining it. What is the radius? The radius is 0.1 millimeter. Density of the kerosene has been given again to you, 0.82, 10 to the power 3. G, I have to carry the G now in SI system. In fact, it is 9.81, but since my answers given are much scattered, I can take it as 9.8 and I can do it with this one also. Then we have cos theta C, which is given the value as 0.9. Rest is the calculation part is concerned. If you do it, you will find your answer will come out to be 5.8 into 10 to the power minus 2 centimeter. Right? Oh, that is meter. And obviously, if I remove this, then it is 5.8 centimeter. So that is your answer, D in this case. So for handling these problems, we have to be faster and we have to be tricky also. Right? Now coming to the next one, slightly changing the, yeah. This is the where you have to get the expression. I read the question for you. The question says that there are n drops this time of radius r each. Coalesces to form a bigger drop of radius r. They combine together. Surface tension is T. The specific heat is given in 1 calorie per gram. The rise of temperature is where J is the joule mechanical equivalent. 1 calorie is equals to 4.18 joule. So this value 4.18 is called joules mechanical equivalent. Out of these options, we have to decide which is the expression for the rise of temperature. But before that, we have to understand one thing. Why there is a rise of temperature? When the drops they combine together, why there is a rise of temperature? Now this is a mixed type of a cases, right? They are mixing the concept of properties of material with the thermodynamics. So this is a trend nowadays in the questions. So let's first of all understand this, then you attempt. One thing is true. I can say that when these n drops they combine, they make a bigger drop. If their radius is r, the radius of this is going to be the capital R as mentioned, and there is a link relation between the two. I can always write R is equals to n to the power 1 by 3 into smaller. This already we have done, right? In that question 27, drops they combine together. We have the similar relation. Coming from this to this, in fact, there is a reduction in the surface area. I'm explaining it with a simple example. You take an orange, let it be a spherical in shape. If I ask you what is surface area of it, you will say, sir, it's 4 pi r square. Agreed. You make a cut from the middle and separate them out. Now what's the surface area? 2 pi r square for this side, 2 pi r square for the other side, but pi r square, the flat one, and from this side also pi r square. So it becomes how much? 6 pi r square. It was 4 pi r square. Surface area I'm talking about. Volume in total remains the same, but surface area increases if I make more cuts. If say pieces are there and you join them, the reverse happens. More surface area in these cases, less surface area here. From the point of the view of the surface tension, because T is given here, the surface tension, you can easily understand that he is talking about the surface energy. So from this stage to this stage, there is a reduction in the surface area. Henceforth, there is a reduction in the surface energy. Where this surface energy is going? If there is no possibility for, say, surrounding to take this energy, the body itself will make use of this energy to increase its temperature. So this is something what must have happened. And here we are combining two relations. One is that the change in surface energy is surface tension multiplied by area. And second thing is the energy, which normally is written as Q in thermodynamics, can be written as mc delta T. Let me not put the T, let me put this theta, that's for temperature. Because T we are taking it for the surface tension, so let's not mix up the things. So these two relations we have to mix up. And this you have to make your point, stronger point, when you have many relations joining in a particular question. But this is a case of a drop, it is not a case of bubble. So one thing is true, that I have to take a surface area of each bubble as 4 pi r square, small r square, not 8 pi r square this time, right? So take the area, surface area, let's do it, right? I'm doing it so that you'll get the idea about it, how to do it. But at the same time, we have to keep an eye on the options given. See these options which are mentioned here. In these options, what I notice, first thing is that I have small r as well as capital R. If I need, I may use it. But there is no urgency to use it in the beginning. But he has used this J. Why he used this J here in the question? Because he has given the specific heat as 1 calorie per gram. So let me keep the CGS system for my whole calculation. It means that when I say specific heat is 1 calorie per gram, that means is 4.18 joule per gram. And this 4.18, that will take care of the J involved in the options. So we have to be tricky. And I on the answers is very, very helpful. So I have to write my answer in the options given to me, not in my own way. That may be correct, but if it is not matching with any of the given option, then I have to convert it, change it. So let's start by in such a manner that we can handle it. How much is the surface energy change? Surface tension multiplied by the area change. How do I get the area? 4 pi is a common factor, please keep it outside. 4 pi, I'm keeping it outside. Later on, it will go from the scene. That's a different matter. What should I write here? The area of all the drops in combination. How many of them are there? N. And what is the area of one drop? 4 pi small r square. Small r square, 4 pi already have taken. Then minus the area of the bigger drop. That is nothing but is equals to capital R square. I hope this statement is clear to you. T is the surface tension. Change of area 4 pi is common factor. I have taken it outside. N. But why I have taken this minus this? Because area here is more and area here is less. So I want to keep this difference positive. Please remember, if you write equation, you must ensure that on both the sides, if both the quantities are positive, very good. If one of them is positive and one of them is negative, it is going to give you a wrong answer. How can a positive number be equal to a negative number? So we don't want to get involved in this type of thing. We are keeping everything positive. Then it must be equated to mc delta theta, because whole energy is used up in heating this drop. So I'll write this equal to qmc delta theta. M the mass. What's the mass? I'm keeping it all in as a CJ system. Please keep that in mind. If I write the mass, I can write the mass of these drops collectively, or I can write the mass of the bigger drop, because mass will remain the same during this physical type of interaction. There is no chemical reaction taking place. It's a physical change we are writing. So what's the mass? Mass will be the volume into density. How much is the volume? 4 by 3 pi r cube. That is the volume of the bigger drop. The whole of the volume. What the density? Water density is 1 gram per cc. That is the mass. This is the mass. Multiplied by the specific heat. J from 4.18. J multiplied by delta theta. Agreed? 4 pi 4 factor will go. 3 will come in the numerator. Now have a look. The moment you get this, can you make out which is your answer? C. But when you say C, you must check, has he kept every other thing same for other options? I have a factor of 3 coming in the numerator. That is a stage where I recognize my answer. Rest is only to verify it. See, 3 will come there, and there's only one option where you have 3 in the numerator. So C is my possible answer. I'm very sure about it. Let's verify it. N r square divided by capital R square, R cube, sorry, minus R square divided by R cube. That is going to be change in divided by J. Check this. The change in temperature, I'm taking everything on that side. 4 pi already is removed. 3 will go here. 3T J. There's no problem, at least for this part. 1 by capital R is there in the option, but not here. No problem. I have a method of doing it. What I can do is, I can put the value of the relation between them. If I'm putting it, if I use this relation as R cube is equals to N R cube, and I'm putting it at this position, I will get this as 1 by small r. So that is a verification which I have done, but otherwise selection is done, say 2 steps earlier. Is it clear? So you can make use of these tricks. These are the tricks. I'll not say that these are the very correct type of a thing, but definitely they save time, right? If you are conscious and if you are careful for the other things, then you, from that stage, you can make out your answer if the need is there. Then coming to the next one. Next, sir. I think this point is clear to all of you. Yes. Solution. Skip it. Graph quotients. The number of graph quotients. One way of checking that whether you have understood a particular formula is not is to give you the numerical based question. Other is to ask you to prove a particular relation. And there's one more way, that is a graph. So we have to, whenever you read a particular formula, you understand all the quantities in relation and think it in three ways: numerical, relation, and graph. What he says, an elastic material of Young's modulus Y is subjected to a stress S. The elastic energy stored per unit volume in a material varies with stress as. Look, there's a relation for the stress energy. See, when I change the dimension of a body, suppose I have a wire, I stretch it. I'm doing some work. Where my work is going? That is supposed to be get stored in the body in the form of what we call as a potential energy or stress energy. So if I write the stress energy per unit volume, the formula is very simple. This is half stress into strain. You have this formula with you. You try to find out which option given is the correct one. This is the energy per unit volume. He mentioned this as E, and this S stands for the stress. This is the formula with you. You have to master the graphical presentation of the formulas. There are good number of questions on the graph formulas. Formula linking with graph, numericals, relations. These are three basic categories of these questions, right? Do you know if there's a linear relation, your graph is going to be a straight line? If it is a quadratic relation, it's a parabola. But we have to check whether the parabola is increasing type or decreasing one. And if I have 1 by quantity related, I'm going to get a hyperbola. Hyperbola. If y is proportional to 1 by x, say y is proportional to 1 by x, I'll get the rectangular hyperbola. Okay, these are some of the typical graphs, but of course, depending upon the situation, you have to look at it. So what do you look from the formula? How this energy is related to stress? Linear, it appears, it is not. Check it. I'm giving you another example, but that will be of great help for handling these problems. Take one problem. Through that, I would like to teach you one very important thing. If I ask you to write the density of the material, what is the formula? Density of this is equals to mass by volume. It can even be area, it can be even be length. Let's not go for it. It's a simple density part. Agreed? Can I say the density is inversely proportional to volume? Check. Suppose I have a spoon having, say, water in it or any liquid in it, and I have a bucket filled with the water again. Both are water, right? In which case the volume is more? In which case the volume is more? Obviously bucket. You can't think of a bucket smaller than a spoon. The spoon will be of very odd size then. But if I take that relation, the density is inversely proportional to volume, I could land up in a wrong answer saying that the density of water is less in this case. See, the volume is more here, but it is water again. The density is going to be same. Where the things have gone wrong, I have ignored this mass. This is one of the most important trick which I am telling you. Whenever you establish a relation, graphically, numerically, or relation wise, you have to keep one thing in mind. If I am connecting one quantity with the another one, I must ensure the other quantity to remain same. If I compare the two, the mass in this case is more. If I count that mass is more, volume is more, it is possible that the density are going to be same for both. Come to this my question, for which I have given you this concept. Looking at this relation, you may land up to a wrong answer. energy per unit volume directly proportional to stress means a linear relation. Your answer could be A or D, and both are not the answer. What wrong has happened? When I relate energy per unit volume with stress, I must not forget there is a term strain also involved in it. Before I go for it, I do a small change in my formula. Half stress, strain I write as stress divided by Young's modulus. If I do that, for a material at a particular temperature, Young's modulus is constant. Strain may not be. Strain will depend upon how much change you have made. But now I have my formula with stress only, and remaining things are all which are constant. This is a perfect format in which you can link the two quantities. That means energy per unit volume is directly proportional to stress square. It means this relation becomes quadratic relation starting from 0, 0. 0, 0 means when stress is 0, this energy is also 0. So which is your right answer in this case? This answer is B, bache. Once again, parabola. Which type of parabola is this? This is where you y have direct proportional to a quantity x with power 2, which gives you the parabola like this. Why not this one? This also is a parabola. But that's the relation where your x is proportional to y square. So this also is to be taken care of. So, but whenever you have options, all options are made with the possibility of the error which normally the students are doing. That is kept in mind. Let's try to read the question setter's mind, what he is judging from you, the understanding. So he will definitely make traps, and you have to save yourself from getting into the trap. First trap was that formula says the stress only with power 1. In fact, it is not, because strain is variable. I cannot ignore the strain. I cannot say the strain. If this question comes with that, yes, the stress variation is there, but strain is kept constant. If they make this type of an say some kind of a situation, then quite probably yes, I say that if this is constant, then there is a direct relation. I could answer it, but otherwise I cannot. Right? In general, I can't. So I hope this point is clear. Remember this thing, and I'm sure not only for this property of the matter, if for the other part of the physics, you can answer the question, especially the graphical question, with this trick. Okay, whenever you have this relation. There are many such situations. Next, sir. This answer. We'll go to the. Yes, we're coming to the connections. That is a tube connected in series. What it says? He says that the liquid is flowing through the two capillary tubes connected in series. Their lengths are L and 2L, L and 2L, and radius are R and 2R, R and 2R. The ratio of the pressure differences across the first and the second tube is. That means there is some pressure difference across the first tube, and there is a pressure difference across the second tube, and they are connected in series. How to proceed? Let's collect the concepts involved in it. First thing, I told you, when the things are in series, one quantity remains constant. Remember, I told you to have its analogy with the flow of charges, the electricity part. Then the resistors are in series, what remains same? That is current. And in our case, what is equivalent to current? Rate of flow. Q remains same. So I'll write one relation simply. I know the relation for Q. Don't write that. Write directly for the situation given. The first one. I'm writing Q directly. That was pi P1 in the first case, R4 divide by 8 eta L. Agreed? That's the relation. Don't write the relation exactly. You put it in the final situation which we need. Next, pi P2. What I should write for R? See, this is 2R. If it is 2R, then that becomes 16. R to the power 4. That information is very useful, I told you. So that comes out to be 16 R4. I'm writing it deliberately on this side. 8, the same liquid is flowing, but length this time is equals to twice of L. This is capital L. Let me put according to what they have given, but anyway, you can use any symbol. So we have a factor of 8. But I should not hurry up to my answer, because both 8 and 1 by 8 are there. Okay, you have to keep eye, as told you. Now read it carefully. Which ratio he is asking for? So he says that the ratio of the pressure difference across the first to the second tube. That means I have to write P1 by P2. If I take this P2 on this side, rest all is constants, they'll cancel out. What is left out? P1 by P2, the 8 remains in the numerator on this side. It is 8. So we should not hurry up. We should do the things faster. Faster doesn't mean that I skip the things. I have to be conscious, as if you are crossing a road where the traffic is running with a very high speed. You have to be careful, and you have to cross the river or the road, right? In minimum times, don't stay on the road for more time. That may be risky, right? The same thing you have to do here. We have to get the answer faster, but not at the cost of the accuracy. Okay? So coming to the next one, sir. Answer, skip it. Yes. The question says the two spherical soap bubbles of radius R1 and R2 coalesces at constant temperature to form a single bubble. The radius R of the bubble is given by. That means the bigger bubble is given by. This bubble means the bigger one. So when they coalesces, two bubbles, they coalesces, what remains same? See why I'm insisting on this part. What remains same? Why I'm saying this? Because I have to write equation. I have to write equation. Volume may not be same. Why so? Because volume depends on pressure, and there is an excess pressure on the in the bubble, right? Can I say at constant temperature the product of pressure and volume in total will be same? See, in fact, what I'm doing, I'm saying that the number of the moles that remains same. And if I write the relation for it, see, there is one bubble of radius R1. Of radius R1, there is another bubble of radius R2, whichever may be more or less, we are not bothered. There is some excess pressure here. There is some excess pressure here, and the bubble we form also is having some excess pressure. Although in this question, it should be mentioned that the external pressure you must ignore. Don't take the atmospheric pressure into the account. There is some air in it also. And when the two join together, the amount remains the same. The amount means the mass remains the same. I cannot write the volume of this plus volume of this is equals to volume of this. I can't do that because pressure is a factor here. Can I say if this contains the number of moles N1 and this contains the number of moles N2 of the air, then the total number of moles in this case is going to be N1 plus N2. See, when nothing is mentioned, even for air, you can use the ideal gas equation, though it's not applicable. You know this. So we can use PV equals to nRT. R is constant, don't care for it. T is constant as is given at a constant temperature. So what else is there? So for this I will write the PV is equals to P1 V1 plus P2 V2. In fact, what I'm writing the number of moles here is equals to N1 plus N2. The constant factor will be out from the scene. Right? This is to save one step. Make a habit, not for the CBSE, for competition type. Don't write the whole equation systematically. Skip out some of the steps if possible. The volume, the pressure. Do you know the pressure in this case going to be 40 by R? Why I'm writing 40 by R? That's the excess pressure inside the bubble. And volume 4 by 3 pi R cube. I don't write anything of this type. I simply write this as R square. Can I write it? See what I'm doing. I'm doing a calculation in my mind. Because whatever the factor constant here, the same is a factor in this case, same is a factor in this case, that will be out of the scene. Why to write and cut it down and unnecessarily waste your time? Volume R cube, pressure will make it 40 by R. R is in the denominator. So effective radius is R square. So this will be nothing but is equals to R1 square, and this is equals to R2 square. I think this is your answer. Which is your answer this time? C. C is your answer. So look at the method, the technique, right? This is a technique to do the things faster. You have to focus on the speed also. Not only on the accuracy. Accuracy is there. Don't compromise accuracy, but save time. Is clear? Next, sir. This is answer. Now, this is from the elastic properties combined with the thermal properties. This is the combination type of the question. What it says, there's a metal bar of length L, area of cross section capital A is clamped between the two rigid supports. Rigid means you can't break it. That remains there. For the material of the rod, its Young's modulus is Y and the coefficient of the linear expansion is alpha. From the thermal property, there is a linear expansion, superficial expansion, volume expansion, alpha, beta, gamma. These are the coefficients. If the temperature of the rod is increased by delta T degree centigrade, the force exerted by the rod on the support is. If I take a rod like this and heat it, then rod must expand. But I don't allow the rod to expand. What then happens? It is something like this, as I have made the rod to reduce its length, to keep the length same. But when I'm doing it, I'm putting some kind of the stress in the rod. And he's talking about what is the force that is developed in the rod, and same amount of the force is experienced by the support. How do I link it? Let's learn this technique. All you know from your thermodynamics background that there is a relation like this. Here the LT stand for the length at T degree centigrade. L0 is the length at the 0 degree centigrade. T is the temperature change. Let me put this as delta T. You can put this T and delta T is your choice. Although this formula is applicable when the change is not very large, right? But let's use this formula. We have only this formula with us. I'm modifying this formula a bit. LT is equals to L0 plus L0 alpha delta T. You take this L0 on this side, L0 alpha delta T, L0 in the denominator is equals to alpha delta T. Look at the left side of your final equation. I simply modified this out. What is this? Change in the length, which I expect because of the expansion, divide by the original length. Change in length to the original length is nothing but is a strain. In fact, I call this as thermal strain, or you simply write this as strain. I have another relation from the mechanical properties of material. Force by area is equals to Young's modulus, change of length to the original length. Stress by strain is Young's modulus. So what then is strain? Delta L by L is equals to, you keep it there, that is equals to F divided by YA. This is strain. This also is strain. Right? What you have done? One strain is expected to come because of the expansion. You didn't allow that. You developed the equal amount of strain to keep the length same. So what the force you expect here? Fya is equals to alpha delta T, and that will give you the answer. And your answer is Ya alpha delta T. You please remember this also as a formula, because they may ask the numerical problem from this. But this is Ya alpha delta T. That is your answer B for this. See, let me quickly revise this. This is the altogether is a part from the thermodynamical expansion, and is a part taken from the mechanical. LT equals to L0 1 plus alpha delta T. If you write this, expand it, and take that change of length divided by the original length, you'll get this as alpha delta T. So this I call as a thermal strain. Whenever the body is heated and is not allowed to expand, then this strain is always there in it. That strain will cause a force, internal stress, and that from that stress relation I'm getting the force. This is very important, that this should not be more than the breaking strength. If I have, say for example, a rod in a, say my roof, a metal say a rod there, and with the change of temperature, definitely the metal rod will expand. So it is under stress. But if that stress becomes more than the breaking stress of the material, the things will crack. So this is one of the very important features, especially for designing purposes. We have to make use of this formula, right? Coming to the next one. Yeah, very interesting question. There are two spherical soap bubbles of radius R1 and R2. One is of R1 and the other is of R2. In contact with each other, they are touching each other. The radius of curvature of the common surface. Look at this surface. This is a common surface. He is asking, what is the radius of curvature of this surface? Who is going to decide the radius of curvature? Who is going to decide? It is a pressure difference on the two sides. What I am saying, if I have a small bubble and a bigger bubble, so this common surface that is between the two will take a shape. Can you tell me out of the two, which of the two bubble will have more pressure, smaller one or bigger one? Inside of the two bubbles, the pressure is more in one of the bubble. Which one is that? Smaller one, because that is 4T by R1 and this is 4T by R2. If the question is like this, suppose I puncture it, I produce a small hole, you know what will happen? The air from this will move to this one, because the air will always move from high pressure to low pressure. Anyway, that is not a part of the question, but this is the one point to remember. Pressure is more here and pressure is less here. So first thing is that the shape is going to be like this. More pressure from this side and less pressure from this side. But this also is surface of a liquid. It must also follow the same rule. Let's see to this. If the radius of curvature is taken as capital R, and on this side, the pressure is 4T by R1, and on this side it's 4T by R2, then I can write a relation 4T by R must be equal to 4T by R1 minus 4T by R2, because the pressure difference is going to decide this radius of curvature, as in the normal case also. So this 40 will be out. So I have 1 by R is equals to R1 R2, and this becomes R2 minus R1. And if you change it, then this will become R is equals to R1 by R2 equals to R2 minus R1, and that is your option number B. in this case. Is it clear? So surface of a liquid is decided by what the pressure difference you have at the two sides. But the smaller bubble has more pressure inside it as compared to the bigger bubble. Right? Yes, next one. Now this is a straightforward formula based question. I want you to do it. It says that the two wires A and B of the same length, please keep that thing in mind, and the same material have the respective radii R1 and R2. Their one end is fixed with a rigid support and equal twisting torque is applied at the other end. Then the ratio of the angle of the twist is, you have the formula with you. The formula for the twist angle has been given to you. The twist angle is directly proportional to torque, right? But is inversely proportional to R to the power 4. From there you can make out. D, correct, very good. No need to have more efforts in it. Very good. That technique is quite useful. See, I have a formula with me which says that the twist angle is directly proportional to torque, says that the same torque is applied, equal twisting torque, so I need not care for it. Same material, same modulus of rigidity, same material and same length. Length also is out of the scene. What else is there? That is the radius. So my twisting angle is inversely proportional to R to the power 4. But I have to be very careful. Then the ratio of the angle of the twist. They haven't mentioned which angle divided by which angle. For this, I will suggest one thing to you. When nothing is given to you, you take the first situation and divide by the second situation. That is a rule. But when you are asked to get the change always we take the final minus initial. This is understanding. Right? There are no rules, nowhere written. When change is required, it is the final quantity minus the initial quantity. But when the ratio is asked for, it is the first situation value to the second situation value. But since they are inversely proportional to it, I think you can easily make out this is, you may have a numerical value also. They may say the radius is taken half of it or twice of it or thrice of it. Then the power 4 factor will help you in that. Right? This is quite simple, but anyway, this is just to give you an idea that how these quantities are related to each other. Next one, sir. This simple one. Yes. A capillary is inclined. In your lecture for the theory, this part was explained, right? Do you remember the formula? A capillary is inclined at 30 degrees with horizontal, is dipped in a liquid which then rises in length of a liquid to 40 centimeters. If the capillary is made vertical, then what is the rise of the liquid in it? It was initially inclined at an angle of 30 degrees. Then it's made vertical. (20 centimeters). And we have to be careful which angle he has given. See, cleverly he has given the angle with the horizontal. This angle has been given to you. No matter whatever the case may be, whether it's inclined or not, this height is going to be the same. That is 2t by r rho g cos of theta c. It is the vertical height this h stands for. Why? Because it's the pressure difference which is caused by the gravity. From that equilibrium, we actually got this equation. So this h is not the length along the capillary, it is a vertical length which is taken from the surface of the liquid. This h. So if this length is 40 centimeter, so obviously this distance, let me put this as h dash. This h dash is related to 40 multiplied by sine of 30 degree. Sine 30 is perpendicular to hypotenuse. So sine 30 is half. So 40 multiplied by half will give you 20 centimeter. So we should remember this, that it is a vertical height in the capillary. At this stage, if I ask you, suppose I have a capillary and the liquid rises to the height, say 20 centimeter in a given situation. And if I take the capillary of the same radius of the same material, but I use only the length 10 centimeter, what will happen to the liquid? Meniscus changes. But in no case, the liquid can ever come out of it by its own. If you do it forcefully, that's a different matter. But by its never it comes out of it. Only thing is that the meniscus that becomes, say, from the more curved to the less curved, and makes the balance at the uppermost position of this capillary. Right? In case of the small size capillary, you must remember it. Right? Whatever the expected length is, if that length is not available, the liquid won't come out of the capillary. It remains up to the top and try to adjust the meniscus. Right? This is the point, remember, an additional thing. Next one. Yes. You can skip this question. This is not from the portion which we have to cover. Yeah. This is the rate of the steady volume flow of the viscous liquid through a thin tube of length L and R under the pressure difference P is Q. He has given you a situation. The rate of steady flow through a series of combination of this tube with another tube of the same length and half the radius if the same pressure difference is maintained across the combination is. Try this one. This is based on the Poiseuille's formula. This I have given you for the practice only, though concept we have discussed. It is based on the Poiseuille's formula, combination of the tubes in series combination. Answer is A. Any other option? There is a tube of length L, radius R, and the rate of flow through it is Q. Q is the volume per unit time, as by our definition, right? Then he says the rate of steady flow. The pressure is P. Let me put this in this way. The pressure difference is P at the end. Now he says that there is a combination of this tube with another tube of the same length, and half the radius. Length is same, but half the radius, and pressure difference is maintained across the ends. The pressure difference is kept same. Now what is the rate of flow? How to handle it? I cannot go blindly that what is a radius change in this case, because he is not asking for this, he is asking for entire of it. See, in series combination, what remains same is the flow. Let me put this as Q dash, which is asking for. Whatever is Q dash in this case, the same is Q through it. Right? This also is required. But in series combination, if the pressure difference is P1 across one and P2 across the other, P1 across one and P2 across the other, the sum of this P1 plus P2 is equals to P. How I got this? If I have a series combination of resistors and current is same through that, the potential difference across one plus the potential difference across other is the total potential difference. Agreed? Let's write the relation, this relation. Keeping this in mind, Q is equals to pi P R4 divided by A theta L. Rate of flow. Poisson formula, quite important for this type of the motion. What then is pressure? Look, I won't care for these two. 8, same in all. The theta, same in all. Length, this also has the same length, same length, same length. I won't care for this. Length also I'll not care. Pi, no need for this. Pressure and radius and Q, this they are all say related to each other, so care for them. I write pressure for the first case. That is my initial situation given. Can I write this as Q divided by R4? Agreed? Let's come to this one. Q dash. What is the radius? R4. Agreed? Plus P2. What should I write? Q dash. And what is the radius of this? R by 2. R by 2. R by 2 whole power 4 means R4. That is in the denominator 16. That will go in the numerator 16. I'm repeating it again. Let's understand this. Let's start from the beginning so that we can get the idea how to handle it. This situation is given to me that there is a tube, length is L, pressure difference is P, radius is R, and say the rate of flow is Q as mentioned in this. Now I connected the same rod with another rod of half the radius, length is same. How do I relate this with this one? He says that the pressure difference is maintained across both of them in combination, same as in the previous case. If you look at this language which he is using, see, if the same pressure difference is maintained across the combination, not individually, across the combination, the whole of it is having the pressure P. So if this is having a pressure difference P1 and this has a pressure difference P2, I say that the pressure difference P1 plus P2 must be the same pressure as in the previous case. So that is my starting point from where I should write the expression. And what I'm doing a bit of trick. Those which are same here, here, and here, I'm not writing them all because later on I have to remove them. For P, using this relation, P is equals to Q divided by R4, rest is constant, don't write that. So I'm writing this as Q by R4. For this situation, I say the rate of flow is Q dash. It is through this as well as this, because in series combination, the rate of flow is always same. Q by R4 in the first case, the same radius. But in the second case, the radius is half R. So when it is half R, R by 2 whole to the power 4 will make it R4 divided by 16, and that 16 will come in the numerator. So what do I have? I have this as Q dash into 17 is equals to Q, but I'm looking for Q dash. I will write this as Q by 17. So that is my answer. That is answer B. You got it? There's a possibility you may do some error, right? Those options are also there. So if you blindly say, okay, the radius is reduced to half, so it becomes 16 times, then you will get trapped. Okay, so we have to save ourselves from getting into the trap. Okay, next one. This is the answer. Yes. He says that two thin tubes of the same length but radius R1, R2 are fitted horizontally. Side by side means series to a bottom of a vessel containing water. This radius, this radius of the single, this the radius होना चाहिए. The radius of the single tube that can replace the two tubes such that the rate of steady flow through the tubes is equal to the combined rate of flow through the two tubes. Let me make the situation. Sometimes they don't give you the figure. If they don't give you the figure, then you have to plan it yourself. That what he's saying. He says that there is a container. There's a container which is having water in it. Okay, water in it. But there are two tubes. And these two tubes are horizontally side by side, not in series, not one after the other. Say, if I make this as in 3 dimension, something like this. So one tube is here, other tube is here, side by side at the same level horizontally, as is mentioned. So obviously, some liquid is coming out from it, say Q1, and so this is Q2. He says that instead of having two tubes, I want to put one single tube. What should be its radius if the length is same for all? What should be its radius so that the rate of flow which is coming out of it, that is Q, is equals to Q1 plus Q2. Let's read the language once again. Situation you have to imagine. The diagram is not given to you, so we have to imagine and we have to understand the things given. Two thin tubes of the same length and radius R1 and R2 are fitted horizontally side by side, horizontally at the same level. One is not above the other, at the same level. Then bottom of the vessel containing water, this radius, the radius of the single tube that can replace the two. Instead of the two, now I have one. Such that the rate of steady flow through this tube equals to the combined rate of flow through the two tubes. That means if this is giving a water flow Q1, this is giving Q2, the combination will give you that same rate of flow. Yes. Can you do it? Relation is there. You have to put certain values to get the answer. See, one thing is sure, the liquid is coming out because of the high pressure at this end, and at the outer end we have the atmospheric pressure. In this situation we must also have the similar situation, so at least the pressure difference is going to be the same. Rate of flow in individual cases Q1 will be equals to pi p R14 divided by 8 eta L. L is same for both, right? Plus, I'm writing Q1 plus Q2. Pi P R24 divided by 8 eta L must be equal to D is the answer. Yes, true. That's correct. I have got the idea how to handle these parameters. Pi P R4, let me put it like this, 8 eta L because of the same length. Then rest is simple. Everything else will go out. So we have R14 plus R24 and then 1/4 of the power. So D is your answer in this case. Is it clear? So now you have understood that how to come out, right? what has been required in this case. Good. We have very few questions now. Yes. Again, say concepts from the two chapters. There is a cube at 0 degrees centigrade is compressed equally from all the sides. When it is compressed equally from all the sides means we are talking about the bulk modulus, right? Pressure, stress, volumetric strain. So you immediately collect from where he is talking, right? External pressure is P. By what amount should the temperature be raised to bring it back to the size it has before the external pressure is removed or applied? The bulk modulus of the material is K and the coefficient of the linear expansion is alpha. See, he's playing a trick here. You have to think in terms of the volume expansion. He is giving you the linear expansion. But no problem. For small changes, we have a relation. The gamma is equals to 3 times of alpha, provided that the changes are small. This we assume because nothing else is mentioned here. So no problem. For volume, we have Vt equals to V0, 1 plus gamma delta T. Agreed? So we have to find out what amount of the temperature to be changed. This we have to check. But anyway, let's open it. V0 plus V0 gamma delta T. V0 on this side, this makes it Vt V0 divided by V0 is equals to gamma delta T. Right? Recognize what is this? That is a volumetric strain. Change of volume to the original volume. And from the relation we have, that is the bulk modulus, that is the pressure stress divided by delta V by V. I'm not using a negative sign deliberately because I know that this quantity is positive. So I'm keeping this as positive. Right? No answer with a negative sign, so there is no problem in this. Why there is no negative sign? Because he already is saying that the rise of temperature. The temperature is to be raised. He's not talking about the temperature change. He has already given you the raised, right? So that's why we're keeping it in this way. But this positive, from here the volumetric strain comes out to be. You take it on this side, K in the denominator, this makes it P by K. Pk, P by K. Anyway, delta T. Delta T is equals to P by K gamma. Which answer is then is the correct one? B. Gamma is not given. No problem. This small trick they normally do. So remove gamma and that makes it P divided by 3 alpha or 3K alpha. So this is how this begin. Next one. Yeah, this is one of the important question which I want to discuss with you. Before attempting this question, one concept, this is again is a mixed category where I have the properties of material mixed with the simple harmonic motion. Do you remember if I have a spring of spring constant K1 connected in series with another spring of spring constant K2, what is its equivalent spring constant? K equivalent is equals to 1 by K1, 1 by K2. Right? I'm mixing this thing there. Let's read now the question with this in background. It says that the one end of the long metallic wire of length L is tied to a ceiling. The other end is tied to a massless spring of spring constant K. The situation is like this. I have this wire of length L and then there is a spring. A mass M hangs free end. There is a mass M here from the free end of the spring. The area of cross section is A. Young's modulus is Y given to you. Then find the time period with which the mass M oscillates if slightly pulled down and released. If I pull it down a bit and release it, it will start oscillating in a vertical plane. And for time period, I have a formula with me. 2 pi is equals to m by k. But which k should I use? That is important. I have this wire, I have this spring also. Spring has a spring constant k, but this wire also will stretch because of the load which you are putting. But it's very interesting, when this load is going down, it is trying to add the tension in the string. But when this load is moving down, it is reducing the tension in the string. Right? If I make the string to elongate, I'm putting stress in it. When I'm taking it back, I'm reducing it. It's just like a spring. So I will treat this wire as a spring. Right? Just like if you have a rubber band, say for example, and you put a mass and you put down, what happens? The mass start also oscillating. With metal wire, it may be not that large amplitude, but it is acting like a spring, assuming the Hooke's law is valid in it. But how to get its equivalent? This is one point. And then finally, we have to calculate the overall equivalent of the whole, this combination. This we have to learn. See, for a wire, I can write force by area, that is stress, is equals to Young's modulus change of length to the original length. This formula I can write easily. Stress is proportional to strain, Y is the Young's modulus. That means force is equals to, A will come on this side, YA delta L by L. I have a similar formula for the spring too. Force is equals to minus K X vector. Obviously, this is a restoring force, that's why there is a negative sign. If I talk about the amount of it, the K will be nothing but is the force magnitude divided by the X in magnitude, the ratio. If I do that, look at this, delta L was the change. So this quantity YA divided by L is nothing but is the equivalent spring constant of a wire. It is K1. I'm repeating this again. This is a concept. If there is a wire alone, forget about this spring for a minute. The wire alone. If there's a wire alone and I put a load in it, it extends by length delta L. Then relation is stress is Young's modulus into strain. From there, I got this expression for force, which in fact is a restoring force to bring it back. Delta L. Force is proportional to a constant into the extension. Force per unit extension is the force constant. Moreover, if this is the force constant of this wire, it is in series with this one. And what is the equivalent of the entire combination? The entire combination equivalent will be equals to K1, K2 divided by K1 plus K2. I already have used that formula, 1 by K equivalent, right? If you solve it, you will get this one. So what then we have? For the first wire case, I have Y A by L into K, that is the spring factor of the spring, divided by YA by L plus K. You calculate the K equivalent and put it in your formula, and your answer in this case will come out to be B. You can check it from this one, K equivalent, and putting it back here will get my answer B. 2 pi under root of M AY plus KL divided by AYK. You can check it yourself, right? This is, I'm speaking because I have to do 2 more questions, right? I'm leaving this for you to do, right? Answer is B. Next one. And how is there? See, in olden times, people used to use bows and arrows. Anyway, question is old, but properties is there. There's a wire of radius R. There's a wire of radius R stretched without tension along the straight line is lightly fixed, rigidly fixed on it. This must be rigidly fixed at A and B, at A and B. Tension in the wire when it is pulled into the shape ACB. It is pulled into the shape. Wire is shaped like this, ACB. Assuming the Young's modulus of the material of the wire is Y and D is very small as compared to L. This though is shown here large in large way, but this is very small as compared to that of L. Right? And we have to get the expression for tension. How do I get it? Tension is a force. Tension is a force. But by this question, I want to tell you or teach you how to do the approximation when the things are given. Right? That is important. Let's take this part of the wire only, because the tension is going to be same, symmetry is there. Its length is L, pulled like this, and if I say the length is L dash, can I say there is an increase in the length? Obviously, there's a side of it and there's a hypotenuse. Hypotenuse is always more, right? For a triangular shape like this. It means by pulling it down, you in fact have increased the length of the wire. But if I can relate this L dash to L, I can find out the longitudinal strain in it. And through the longitudinal strain, I'll go to the stress. And from the stress, I'll go to the tension. This is the route which I'll take. But how will I relate it? I write this as L dash square is equals to L square plus D square. Agreed? So this square will be out from here. L square plus D square under root of it, I'm putting is half. Okay. If I take this L out, I'm taking in fact L square, but because of this half, when you take it out, it becomes L. 1 plus D square by L square. With the power half is there. See, this is a series. And mathematics, now you know how to expand this series. But our concern is that for the case when D is very small as compared to capital L. If D is very small as compared to capital L, this quantity is going to be very, very small. And if you expand a function like this, 1 plus x to the power p, p is the power, then there are many terms, 1 plus px, then so and so on. But with increase in the number of terms, the power of x is increasing. If quantity is very small, its higher power becomes even smaller. 0.1, if you do the square of it, it becomes 0.01. It is further very small. So I ignore all of them. But under the condition, D must be very, very small as compared to length L. That's the condition to be followed. If that is the story, then I can simply multiply this half here, and I can write this L dash as L 1 plus half D square by L square. Agreed? Open it up. L plus half D square by L. 1L will be out from this L square. This L go that side. L dash minus L. That is a change. 1 plus half. Oh, sorry. This is now half D square by L. If I divide by L, that will become L square. So can you recognize this? Strain. And if I multiply it by Young's modulus, then what this is? Stress. Stress is force per unit area. If I multiply it by area, then that is force, and that is a tension. Only thing is that the area in this case is written as pi r square. If you check it, this is going to be D square by L square with the power 2. C is your answer in this case. Is this clear? So this is how these properties can be taken. Can I take the question from the other centers? We have little time left out. Okay. Ice cube is gently placed at the top of a liquid filled in a beaker to the brim. What will be the effect on the level of the liquid in the beaker? This I covered. In fact, nothing will happen. No change in the level will be there. Look at this. Why there is no change? See, this is a beaker. Let me make it like a beaker. And this is a piece of ice. And this is the water. It is floating. But see, if it is to the brim, we'll go to the top of it. In fact, the capacity of the beaker, in accordance to the capacity of the beaker, we don't have the water in it, because this much of the portion which I am now shading is in fact is not water initially. If I say this is the volume V, I call this as additional volume in the beaker. This is water, but this is the volume which is displaced by the ice in order to make its own place there. How do I get it? If I take the mass of the ice to be m, then the weight mg is to be balanced by the buoyant force, and the weight mg is equals to v rho w into g. I get the value of this v as m divided by rho w. This is the additional volume. It is not water. In fact, it is a volume occupied by the ice at the time when it is floating. What happens when the ice melts? When ice melts, it forms the same amount in mass, same amount of the water as its own mass. Mass of the ice is equal to the mass of the water, is equals to density of the water multiplied by the volume of the water. So how much volume of the water I get when it melts? It is exactly the same. If you check it, this VW is equals to m divided by rho w. This also is m divided by rho w, means that when ice melts, when this ice melts, it forms a water that will fill up this much of the volume, and the level of the water will remain same. That is the answer for the first question. In question number 16, can you see the whole of the extension produced in the spring will not be equal to the change in the length of the wire. So kx is not equals to the yd. Okay, let me tell you one thing. The formula which we have used for the question number, that is 16, I am explaining it. It is quite true. But the formula which I have used is taking care of it. This is K equivalent. This is K1 and K2. I agree with you. Yes, the length of this wire, let's this change is equals to x1. And the spring has changed its length to x2. You agree with this? They are not same. They may be same under special condition, but in general they may not be same. If I ask you what is the increment in the combination of the two, you will say that this is equals to x1 plus x2. Suppose this wire extends by 1 millimeter and spring extend by 3 millimeter. The total extension is going to be 4 millimeter. But in series combination, the force or the tension that remains same, because it's a massless spring. So if I write x from the formula f is equals to kx, I can write this as x is equals to f divided by k equivalent as a whole. For x1 it is equals to x divided by k1 and f divided by k2. So this ff is out. So I have 1 k equivalent, 1 by k1 and 1 by k2. So even if the extensions are not same, this formula holds good. And we have used in fact this formula. So that's why we have taken care of the variation of x1 and x2. They may not be same, right? So that has been taken care of. Question number 2. Can we come to the question number 2? I don't remember it. That was for some energy, huh? Question number 2 must be on this. No, go to. Yeah, this one. The work done in blowing the soap bubble. See, here the main concept is that when you talk about a bubble, the surface is not having an area 4 pi r square, rather it is having an area of 8 pi r square. See, bubble has two surfaces. One is from the inner side, other is from the outer side. So in fact, the surface area is 8 pi r square. 8 pi r square. Take care of this. This is very important. It was of 2 centimeter initially. It changes to 5 centimeter finally. And he's asking how much is work done. Work actually is done in order to increase its surface area. So how much is the increase in the surface area? If I put this as delta A, this is equals to 8 pi R2 square minus 8 pi R1 square. This is given in centimeter and answers in SI system. So we have to be careful for the dimension part of it or unit part of it. 8 pi R2, the 5 centimeter, that is 25 into 10 to the power minus 4 in meter square, and 2, 4 into 10 to the power minus 4 again in meter square. This is a change in area. If you multiply by surface tension both sides, I'm getting the change in potential energy which is equal to the work done. This all we have to calculate. What I told in this particular case is that sometimes there is no need to solve it completely. Sometimes we are getting an idea that which options cannot be the answer. Anyway, you can put the value of the surface tension 6 into 10 to the power minus 2, 8, and this pi can be taken as say 3.14, or you can write this as 22 by 7, just to keep it simple. This is 25 minus 4, that gives you 21 into 10 to the power minus 4. Rest is a mathematics, but this helps you a bit. Removing this 21 from here, that makes it 3. So you can save some of the time. Minus 4, minus 2 cannot be the, say minus 6 cannot be the possible answer. So that's why we removed the option B, option D from the scene, and then rest is calculation for this. One more question. Question number 13. So I have to go to the question number 13. Yeah, vessel of cross section. Okay, you want this question to be done? Okay, well, let's do it. It'll take some time for me to do, but see what it says. A vessel of cross section of area A contains a liquid to a height h1. This is a vessel which contains the liquid to the height h1. Its area of cross section is capital A. If the hole is cut there at the bottom, having the area which is equals to small a at the bottom, then the time taken for this liquid to come out of it up to the height h2. How much time will it take? Actually, this is a question from the Torseley's equation. So I skipped that one. That's why let's do it. See what happens. Let's take some in-between situation. Let's take some situation where the liquid is up to the height x, any unknown height, anywhere in between. Say with this height, the liquid will come out with a flux velocity which is equals to 2gx under root. This is the Torseley's equation. But you treat that this is the inlet of the pipe and treat this as the outlet of the pipe. From inlet to outlet, the flow will be A, the area of cross section. The velocity with which this level is going down is equals to dx by dt is equals to small a 2gx, that is the velocity. Since we are looking for time, you take the dt on this side, and rest is on this side, that is equals to capital A, small a, dx, take under root of 2g on this side, and under root of x, that is x to the power half on this side, and do the necessary integration for it. There's a separation of variable I have done from 0 to time t, and from this height, say h1 to the height h2. It is x to the power half, in fact is x to the power minus half. So when I integrate this, I will get this as capital A by A, under root of 2g will be there already. X to the power minus half, integral means power is increased by 1, that makes it x to the power half, divide by half. Divide by half will take this 2 up, and then we have to put the limits h1, h2. And rest is the mathematics, right? You can put the value of this. In fact, there is one point here I would like to mention one thing. For dx by dt, you have to put a negative sign. Why so? Because with time the x is decreasing. So when you put the limits with one additional sign, you'll get h1 under root first and then h2 under root at the second place. So that will give you the answer with D option, I think. This is 13th. This is the answer B. Is answer B because this 2 and this 2 will go up, will make under root 2 in the numerator. Capital A by A is here. So your answer is B in this case. Is it clear? Yes. That's all. Huh? Able to complete. Huh? Thank you very much.